Alright. Hello everyone. Welcome to the problem session. So this week we looked at sliding mode control, and it's generally pretty easy. I mean, you just cancel out the dynamics and then design your controller, and then you're done. So I'm gonna do a quick recap of that, and then I'll go through an example that showed up on a final exam a couple years ago, just as sort of a numerical example. They're all kind of the same, so just to show you how it's done. And then towards the end, I'll show some Simulink plots that are both in the example that I'm going to do and also in your homework. So hopefully that turns out. So to do sliding mode control formally, we pretty much, if you recall in lecture, ended up with some. So we have x to the mth derivative is some function of x plus u1 and u2. We let u1 is equal to our best estimate of the dynamics, and then we're left with just some 1 over s to the m plant equals to u2. And if we now define a sliding surface on this s, is some c times x. So we said this was where we want to put the poles, essentially, of our kind of sliding surface. And for a third order system, you get something like lambda squared plus 2 lambda plus 1. Of course, they don't have to be here. This is assuming we're putting all the poles at -1. It could be something else. So then you end up with u2 is negative c times over. So that's basically what we ended up with.
So you're going to get two different expressions for u2 then, right? One is this x to the n, and the other is when you evaluate that expression.
Yeah, so this is what we choose our controller to be.
Okay.
Right, so after we canceled out all the plant dynamics, we're left with a 1 over s to the m plant. Right? Now we want to design our controller. And for sliding mode control, this is what we're designing our controller, how we're designing it. That makes sense?
Oh, okay.
Just
Yeah.
like when we had, our linear systems before, we had, like x double dot plus some type of x dot plus g equal to some u, right?
Mm-hmm.
So, like, this is how we're designing our controller.
Okay, I see. So they're all equal to each other, basically.
Yeah. So what we're doing afterwards is we're putting this, back into everything, and then we come up with our final kind of closed loop solution. So that's all I have to say about that part. Oops. Do an example. So the context of this example is, so Mbari has these AUVs that go and map the seafloor, and they have to kind of fly really, really close to the seafloor at around 2 meters altitude, and you're trying to maintain a constant altitude. So we're basically working with a simplified plan that's, say, h dot is c times theta and theta dot is. So here we're trying to maintain a constant altitude, that's h, and theta is kind of, here's our vehicle, and over here is our h, and then here's our theta, right? So this thing is going with some velocity c, and to approximate, to simplify the plant, we're saying that the change in altitude is just kind of our velocity times theta, assuming theta is small. And then our theta dot can be expressed as some input. This is our thrusters, plus some unknown disturbance, right? Because of all types of effects. So if we're too close to the bottom, we get some currents come up that could affect the thrusters. So this d is a function of h, sort of. Right, but we don't know what it is. But let's say that we know that within a bound, within this bound, we know that our disturbance is bounded by some value d dot.
How can h be negative? How can h be negative?
So we can define h at any dot, right? So if this is our reference depth, then this is our h. So we're essentially, so we're trying to zero it out. Essentially, we have some reference h. We're trying to zero it out. Okay. So let's see what we can do with this first. This is kind of funky, so I'm just gonna first differentiate this and get the plant in our proper, usual form. So h double dot is c theta dot, which equals to c times u plus d. So this is some cu plus cd. So now we look at this, we might say, well, this looks kind of like a 1 over s squared plant, except we got this thing over here that we don't really know anything about. So what we can do is let's ignore it for now. Okay. So if we say that this cu, I'm just going to redefine it as some u tilde. And we're going to design our controller based on the plant h double dot is u tilde. So if we had, turns out to be a really simple dynamics equation. If we had other stuff on this side, like in your homework, then you simply split this up into u1 and u2 and cancel it out like that. So now we have a sliding surface. Say we want so we have the face plane. Say we want to slide along the surface S, and S is given by h dot plus lambda h. So how do we go about designing what u is? Well, first of all, so we could put it in that form, right? but in this case, so we would have h dot, and then our F matrix would just be 0, 1, 0, 0. Our G would be 0, 1. You know, and our C would be just 1, 1. Right? So you could work this out, and you will get U tilde. What you could also do is, what we really want is for when it comes onto this sliding surface that it never leaves the surface. So we want S dot equal to 0. So let me just write it here. So S dot is H double dot plus lambda H dot. H double dot can be approximated by our U tilde. And this whole thing is 0. So we get U tilde is negative lambda H dot, which is the result we've seen before. So there's two ways of doing this. This is the formal way, right? And you should do this in your homework. And this is kind of the way we've done it before. Okay, so now that we have that, we have so this is not going to be enough, right? Because we need, if it, because of our disturbance, if it comes off the surface, we need a way to kick it back onto the surface, right? So we add delta signum of S, right? So if it's off the surface, we kick it back. So this becomes our controller in this case. So what does delta have to be? Right? How can we prove that this controller is stable with our real plant that's over here? So let's see. So we set up a Lyapunov function, or something like it. So we can have our V equal to half S squared, so that's the sliding surface, and V dot is S dot S. So this gives us where's my S? S equals H dot S. So this is H double dot plus lambda H dot and S. So now we can put in our real plant over here. So this is U tilde plus lambda H dot times S. Sub in what we have. Oops. Alright. I forget. U tilde plus this term. Right. So yes. these guys cancel out, and we have this. Delta sigma S plus D times S. So, what do we want this to be? So we want this, our V dot, to be less than 0, right? To prove it's stable. So that means, so if we look at this expression, we can see that when S is positive, it's up here. So if this is positive, then this first term has to be negative. So this will be negative if, so this is positive, that means the sign is positive. So when S is positive, we want CD minus delta to be less than 0, right? So our delta greater than C. And when S is negative, so this is negative, this is now negative, this whole thing is now plus delta. So S is negative, that means we want this term to be positive, so it's, so when S is less than 0, we got CD plus delta greater than 0. So, tricky thing here is that we don't know what D is. D could be positive or negative. But we know that its absolute value has to be less than D naught. So over here, so delta is a positive number, right? So so the maximum, so the worst case for this one is when D is equal to D naught. And for here, if we make delta greater than CD naught, then this is satisfied, right? And over here, we're worried when D is a negative number, because then this becomes positive. And so again, so when D is now negative D naught, right? Then, so when D is negative D naught, we have delta greater than C D naught. So you end up with the same condition, that delta should be greater than this C times D naught. Any questions?
So what made you decide to stop ignoring CD at that point?
Yeah, so we have some disturbance in our plant, which we don't know. To design the controller, we ignore that disturbance because we're going to assume that this extra term is going to be robust enough to kick all the disturbances back into place. Okay. But to prove that this controller is actually stable using the real plant, that's when we have to put in the real plant and our controller, and when we do the Lyapunov analysis. So when we're designing the plant, we're using kind of the ideal case. Mm-hmm. And when we're analyzing it, we're putting in the real plant to kind of help us choose what these values have to be, how big the delta has to be. So, I mean, in real life, you wouldn't know exactly what these numbers are, right? So you would just kind of, put this on some knob, right, and turn up the knob until it works, right? But this is how we kind of analyze it. Yes.
When you say stable, does it mean stable as in it's following the sliding surface, or stable as in it's not blowing up?
So I mean stable as in it will be able to reach this surface and then go down along the surface. Because it's inherently, let me see. So when you have a 1/s squared plant, right, and you have some kind of a switching line, right, this is now essentially a stable system, right? So recall our phase plane analysis. You could get trajectories that look like this, right? But when we do this, if this isn't big enough, then this is not gonna, then like the trajectory are not gonna come back to this line. So they will have the same slope as this, right? But they're not gonna be able to reach the line. So you'll end up with something that maybe comes here. Say you start over here, right? And your delta is not big enough. It's just going to drive you over here. Right? It won't have enough power to move you to the right.
What if you just see something where it like circles into the origin or something weird, rather than sliding along the surface? Is that?
So sliding mode control, we're basically setting it up so that it will slide along the surface. Right? Of course, you could do something else. That would be a different type of controller. Right? And the great thing about this is that we can, for a second order system, we can follow the trajectory of a first order system. Right? And for an nth order system, you can always follow an n-1 order system. So now I want to show you what happens. So in this case, when we set this delta to different values compared to this stuff. So I don't know how well this is going to work, but I'm going to try to plug in. do something with. Oh, I'm getting something. There you go. So I made a little Simulink thing, and let me just see how long. Oh yeah, that does not show up at all. So I apologize to the people who are watching.
Or the actual. Might have to post it online.
Yeah. Well, I can post this online. I can't post the other stuff. I was gonna show you.
You can post like a PDF of the plots.
Yeah, I could do that.
I take it it's not showing up on video right now.
It's not. No. But anyway, so here I've set. I've set our lambdas to 1. This is our delta. I've set it to 0.1, just some random numbers. And this is our disturbance. I'm just gonna set it to something that's manageable. And then just a sec. I'm trying to plot. So here we end up with something that started from -1, 0, and it's following the trajectory down. Just okay. Now let's make this bigger. Okay. So you see we're still converging to the line. And now let's make it more than 0.1, so like 0.11. Okay. So now our disturbance is bigger, and we have this constant that's always feeding us there. So our delta is not big enough to get us back. So what I also have is, so in your homework you have these inverted pendulum, right? And you're also assuming uncertainty. So for that, so I think the epsilon over there was maximum 0.1, right? And if you simulate the system using different epsilons, you can get things that are like this. So here we have our theta position, and if we So this is for epsilon at 0, and this is 0.1. So you can't take a picture of that. Don't take a picture of that. Actually, yeah, why don't, you can take a picture of that if you want.
Mine looks infinitely better than that.
I'm sure it does. And
That's why I was asking.
so this is just one case, right? So if we look at it on the base plane, you get something. If you start off here, here's our sliding trajectory. It's stable until you hit an epsilon of more than that. Sorry, what were you gonna say?
Yeah, the reason I was asking is because I made epsilon really big and I saw like a giant circle towards the origin. That kind of confused me.
What was your initial conditions?
0 for theta dot 1 for theta.
1 for theta. So that may be too big.
So we're assuming the state pi
10 pi over 1/8. That's 10 degrees, right? Or 10, yeah.
Right. But if you put in just 1, then it's...
Yeah, that's one radian, right?
Okay.
1 radian is like 60 degrees, right? So,
Okay.
yeah, so if you zoomed in, maybe you'll be able to see something, but that's kind of out of the bounds of our assumptions.
Did
Hey,
you go to the other part?
this
This
one?
one is, oh, okay, it's done. Okay. So you did both phase plane and
Yeah.
position first.
And there's something else. Let's see. It's kind of what our U looks like. You apply some control and then it zeroes out. Except for the case
Should
when
be
it
really
goes.
close to the
Choose delta really close to the bound.
Did you do that? 'Cause,
Yeah.
like, I'm not seeing as much variation in epsilons, but it might also be the distribution, so delta's too big.
Okay. Yeah, that's possible. Yeah, if you're always whacking it, then it's kind of just bang bang controller, right? Yeah. So, yes, I mean, if you want to post any of these, feel free. Again, I don't think you'll be able to see anything on the video. But yeah, I think that's all I have.
This question that you worked through,
Yeah.
this is the one that was on the midterm, or...
Yeah, so this was on a final a couple years ago. But all of the sliding load control tends to look something like this. I mean, it's very easy once you cancel out everything, right? You just design all the controllers the same way. But it assumes that you have some good estimate of what your plant looks like.